All right, let's talk about the most powerful eye on the universe we've ever built, the James Webb Space Telescope. It is sending back pictures that are completely changing what we know about the cosmos. And today, we're going to break down what it's already found and the huge questions it's trying to answer next. Let's dive in.
So here's our journey. First, we'll get into what makes this telescope just so different. Then, we'll talk about its superpower, seeing in infrared light. From there, we'll actually watch stars being born and dying, look back in time more than 13 billion years, see how scientists are basically hunting for alien air, and finally, we'll meet the one planet out there that might just be another Earth.
And really, this quote from NASA just nails it. We're not just getting sharper, prettier pictures here. Every single image Webb sends back is a discovery. It's a new piece of the cosmic puzzle that, until now, was totally invisible to us.
Now, making this happen, well, it was a massive undertaking. We're talking $10 billion and a full 25 years just for design and development. This isn't just another telescope. It's one of the most ambitious things science has ever attempted. So what makes it worth all that?
Okay, so let's get into how this incredible machine works. See, to catch the faintest, oldest light in the universe, you can't just build a bigger telescope. No, you have to completely rethink where you put it and what kind of light you're looking for.
And it all comes down to one thing: temperature. You see, unlike Hubble, which orbits the warm Earth, Webb is way out there, about 1.5 million kilometers away, orbiting the sun. It hangs out at the special spot called the second Lagrange point, or L2. You can think of it like a perfect gravitational parking spot. It lets Webb use its massive sunshield, which is the size of a tennis court, by the way, to block all the heat and light from the sun and the Earth. Why go to all that trouble? Well, to see the faint heat signatures from the dawn of time, the telescope itself has to be unbelievably cold, like just a couple of degrees above absolute zero. And being that cold is what unlocks Webb's superpower, its ability to see the universe in infrared light. And I'm telling you, this isn't just some minor technical upgrade. It is the key to seeing parts of the universe that have always been completely hidden from us.
Here's an easy way to think about it. You know how cosmic dust clouds are like a thick fog? Well, the visible light our eyes see gets totally blocked by it. But infrared light has a longer wavelength, so it sails right on through. It's kind of the same reason that radio waves can go through the walls in your house. Webb's infrared sight literally makes the invisible visible.
But Webb doesn't just have one way of seeing in infrared. It's got two different eyes. Its near-cam gives us those jaw-dropping, viral images you see everywhere, full of amazing detail. But then there's the miri-cam. It uses even longer wavelengths to peer through those same clouds, revealing the hidden stars being born inside. It's like having regular sight and X-ray vision at the exact same time.
So what can you actually see with this new power? Well, for starters, the entire life story of a star. Let's take a look at one of Webb's very first images, the Southern Ring Nebula. What you're seeing here is a star dying. This is basically the biography of a star, like our sun. It starts in a nebula, lives for billions of years as a normal star, then it swells up into a red giant, and then it sheds all its outer layers as a planetary nebula, which is exactly what we're looking at here. And what's left behind is a tiny collapsed white dwarf. And here's the wild part. This is a sneak peek of what's going to happen to our own sun in about 5 billion years. And for the very first time, we can see what's going on right at the heart of this cosmic light show. The dying star has been puffing out these huge shells of gas and dust for thousands of years. But thanks to that miri-cam we were just talking about, Webb sliced right through all that haze and revealed a secret. There isn't one star at the center. There are two, locked in a gravitational dance, something we never knew until now.
Okay, that's amazing, but Webb can do something even more profound than just see across space. It can see back in time. Because it takes light so long to travel across the universe, looking far away is literally looking into the past. And Webb is, without a doubt, the most powerful time machine humanity has ever built.
Take a look at this. This is Webb's first deep field, and it is just mind-bending. Some of the light in this single image has been traveling for 13.1 billion years to reach us. To get this shot, Webb just stared at one tiny patch of sky for 12.5 hours. And it used a neat trick called gravitational lensing, where the gravity of a huge galaxy cluster in the foreground actually acts like a magnifying glass, bending and boosting the light from the even more distant galaxies behind it. And here's the secret code. The redder a galaxy looks, the farther away it is, and the further back in time we're seeing it.
And then there's this incredible image of Stephan's quintet. Now, it looks like 5 galaxies, right? But what's so cool is that only 4 of them are actually interacting. The one on the left is actually way closer to us, about 40 million light years away. The other 4 are almost 300 million light years away, and they're all tangled up in this cosmic dance. For scientists, this is like a perfect laboratory for watching how galaxies smash together and evolve over time.
But look, Webb wasn't just built to take beautiful pictures. As amazing as they are, its most revolutionary mission is to do something totally different, to actually analyze the light from distant planets and hunt for the chemical building blocks of life.
The science is called spectrography, and honestly, the logic behind it is pretty simple. Think about a leaf. Why is it green? Well, its chlorophyll soaks up red and blue light, but it reflects the green light, which is what we see. An alien atmosphere works the same way. The molecules in the air will absorb very specific wavelengths, or colors, of the starlight that passes through it.
So here's how it works. Webb waits for a planet to pass in front of its star. It catches the starlight that filters through the planet's atmosphere. Then its spectrograph splits that light into a rainbow, and it looks for which specific colors are missing, the ones that got absorbed. Every molecule has a unique barcode of light that it absorbs, so by seeing what's missing, we can tell exactly what's in that planet's air. It's like finding a chemical fingerprint made of light.
And it works. Webb has already made a huge discovery. It looked at an exoplanet called WASP 96b over 1,000 light years from here, and it found the undeniable chemical signature of water. Not just that, but evidence of clouds and haze too. Now, before you get too excited, this planet is a gas giant, and its surface is over 530 degrees Celsius, so yeah, definitely not habitable. But this was a massive proof of concept. The technique is real.
So the big question is, where does Webb point this incredible new ability next? Well, let's meet what many scientists think is the single best candidate for a habitable world we have ever found. Its name is TRAPPIST-1e.
And just look at these numbers. It's almost spooky how similar this planet is to our own. Its size, its mass, its density, its gravity, all incredibly close to Earth's. We already know it's a rocky world, and it orbits its star right in the middle of the habitable zone, that sweet spot where temperatures could be just right for liquid water to exist on the surface. This is our best shot yet. So here is the mission. In the coming months, Webb is going to stare at this planet and analyze its atmosphere in incredible detail. And it's hunting for a very specific cocktail of gases: carbon dioxide, methane, and water vapor. Now, finding that mix wouldn't be 100% proof of life, but boy, it would be a powerful sign that some kind of biological process could be happening on that world. And that really just leaves us with this final massive question. For the first time in the history of our species, we have a tool that is actually capable of finding evidence of life somewhere else. If it finds those chemical fingerprints, that's not just another discovery. It would change everything about how we see ourselves and our place in the cosmos. So, what do you think happens the day after that news breaks?